Okay, so we're very happy to have Kasia Kowalik from the University of Warsaw here to talk about the chain-antichain principle and proof size. Go ahead.
Yeah, thank you very much, Atar and Roman, for giving me opportunity to talk at this seminar. I'm very glad to present my work. This is basically a part of a bigger project with Leszek Kołodziejczyk, my supervisor, also Keita Yokoyama, Tinlok Wong, Marta Fiori-Carones. So yes, the title is the chain-antichain principle and proof size. So yeah, I will explain slowly what this title means. So the chain-antichain principle, CAC, says that for every partial order on natural numbers, there exists an unbounded set S, which is either a chain or an antichain in this order. So this is a Ramsey theoretic combinatorial principle, well known in reverse mathematics, and it is immediate consequence of Ramsey theorem for pairs and two colors. And the main theorem for this, I wanted to say evening, at least in Europe, is that RCA0 star plus CAC is polynomially simulated by RCA0 star with respect to pi03 formulas. In particular, it does not have non-elementary speedup for pi03 formulas over RCA0 star. So don't worry, I'm going to explain what this theorem precisely says and what is the argument to prove it. So the plan for the talk is as follows. So firstly, some formal background. I guess that for most of you, at least half of this will be well known. Maybe for some of you, all of this will be very well known. Then motivation for this work, namely the case of RT22, Ramsey theorem for pairs and two colors, with some analogous results. And then the main part of the talk will be explaining the proof of the result. By the way, if you have any question, please do interrupt. I'm happy to answer, to clarify everything that will be needed. So we work in second order arithmetic, where by L1 I denote the purely first order language. L2 is language of second order arithmetic. So the capital letters are for set variables. Models for L2s are of this form, whereby M is thought of as set of natural numbers and X is some family of its subsets. We have the usual arithmetical hierarchy by which we distinguish between these classes with superscript 0, which allows set parameters, and those without superscript are purely first order. And traditional base theory in second order arithmetic for reverse mathematics is RCA0. It consists of three groups of axioms, so basic properties of operations on natural numbers and order, PA minus, comprehension scheme for delta 0, 1 formulas, and induction scheme for sigma 1 formulas. And the first order part of RCA0 is I sigma 1, and probably recursive functions of RCA0 are precisely the primitive recursive ones. So the stuff well known, but we are interested in weaker base theory, namely RCA0 star, which is obtained from RCA0 by replacing sigma 1 induction with delta 0, 1 induction, and the axiom exp asserting that exponentiation is a total function. because we don't assume that we don't have exp in the language, and normally you need I sigma 1 to prove the totality of this function. So this theory is not a new invention. It was introduced by Simpson and Smith in 1980s, and it is mostly used to identify theorems that are equivalent to I sigma 1. So when you work in RC0, you cannot really trace non-trivial uses of sigma 1 induction in your proofs. So they studied some theorems in countable algebra. But why do we want to perform reverse mathematics of combinatorial principles over this weaker-based theory? So it turned out quite recently in work of David Belanger that it might be relevant for some results over RC0. And yeah, that was our hope when we started to look at this weaker-based theory. We wanted to learn something about RT22 over RC0 star and maybe find some analogies to study it over RC0. And yeah, the first order part of RC0 star is B sigma 1 plus exp. So it is definitely weaker than for RC0. And the probably recursive functions of RC0 star are precisely the elementary recursive ones. So from some foundational, maybe philosophical point of view, some people would like to see some results over this weaker based theory. And yeah, important thing, maybe not really for this talk, but anyway, the feature of the difference between those two theories is that over RC0 star, yeah, RC0 is equivalent to the statement that every infinite set has arbitrarily large finite subsets. So there are models of RC0 star where this statement is not true. So let us look how the world may look like where sigma 1 induction fails. So we have a model of RC0 star M, and failure of sigma 1 induction means in terms of model theoretically, that there exists a sigma 01 definable proper cut. So here you have the guy I. It is defined by some sigma 01 formula. And every time you have such a cut in the model of RC0 star, you have an unbounded set A, which is in this second order part of the universe. It belongs to this family X of subsets of M. And it is unbounded, and it can be enumerated in increasing order by the cut I. So its cardinality is strictly smaller than that of whole universe. It has finite subsets only of those cardinalities that are in the cut I. And important for us will be that this set A divides our universe into I many finite intervals from A0 to A1 and so on and so forth. There is nothing special about this first element of A above the cut. It's just to make this picture more clear. And we can, in such a model, we usually have many sigma 1 definable cuts. So we consider a cut I01, which is defined to be intersection of all sigma 01 definable cuts. And this guy, I01, may or may not be sigma 01 definable itself. And yeah, we will later consider both cases. Also, I01 may be equivalently defined to be the set of those x's such that every unbounded set contains a finite subset of cardinality x. Yeah, do you have any question at this point? So I would like you to keep this picture in mind. Like actually, this.
Kasia, just a short, quick one. This applies to all models of where sigma 0 induction fails, regardless of cardinality, right?
Yes, yes.
You do not assume anything about how large the model is.
No, anything.
Right.
Yes, that's all about our base theories. So now context for this work and something about RT22. So just as a reminder, Ramsey theorem for pairs in two colors, RT22 says that for every coloring of pairs of natural numbers with two colors, there exists an infinite, infinite, I mean unbounded set H, such that the coloring C is constant on pairs from this set. So yeah, it should be written here unbounded because actually when we don't assume sigma 1 induction, there are, well, two notions of an infinite set. One is unbounded and the second one is of cardinality n. And if we changed here the requirement, then we obtain a stronger principle, but that's not the topic for today. So RT22 is probably one of the most important theorems in reverse mathematics. So it's maybe the most prominent case of important mathematical theorem that turned out to be not equivalent to any of the big 5 subsystems of second order arithmetic. So it is a very natural and important question to ask what are the first order consequences of RT22. So over RC0, we know by work of Patey and Yokoyama that RT22 is pi03 conservative over RC0. The hypothesis is that its first order part might be B sigma 02. Well, it is at least, B sigma 2, but it's strictly below I sigma 2. Yeah, but nobody, knows at this point. And we have the same theorem, but for RC0 star. And it was essentially proved by Keita Yokoyama, and it's written down also in my work with Leszek and Keita from last year. And yes, when you have conservation results, you may ask further and want to know whether your additional axiom allows you to prove sentences from a given class with shorter proofs. So yeah, we ask about length of proof, and let me introduce two notions to speak formally about it. So if you have two theories, T and S, and gamma is a set of sentences in their common language, then we say that T is polynomially simulated by S with respect to gamma if there exists a polynomial time algorithm which for every proof of a sentence in gamma in T outputs a proof of this sentence in S. So in particular, in such a situation, for each proof of gamma from big gamma in T, there is a proof in this, in theory, S of this sentence of at most polynomially larger size. And the opposite situation is this. We say that T has non-elementary speedup over S with respect to gamma if for every elementary recursive function f, there exists a sentence in gamma and a proof of this sentence, delta, in theory T, such that every proof of gamma in S has size greater than value of this function on length of delta. So the sizes of proofs of some sentences explode in this weaker theory. So what is the answer for this question for RT22? It depends on the base theory. So Leszek, Lawrence, and Keita showed that RT22 is polynomially simulated by RCE0 with respect to pi03 sentences. And the proof was obtained by method of forcing interpretation, formalizing construction of a generic cut in a model of RCE0. I'm not going to say anything about it now because I'm going to use similar methods later for CEC. But the same team proved that over RC0 star, RT22 has non-elementary speedup with respect to, it's even better. It was copy-paste, sorry, for sigma 1 sentences. So for a pretty simple stuff. And let me.
Kasia, can you go back to the definitions of those two ideas?
Yes.
Just give me a second. Okay, thanks. That's. I just want to read it one more time. Go ahead.
Yeah. Okay. Please stop me every time I'm too quick. Yeah. Thank you. So both of these results are in the same paper, which will be listed in the last slide. But let me. It's a very nice proof. It combines a lot of facts from slightly different areas, and it's very elegant. And actually, it will be also the crucial point of it will be a motivation for the rest. So this is how it roughly goes. The lower bound for a finite version of RT22 is exponential. So this means, this arrow notation, that there exists a coloring of pairs with two colors of a set of cardinality 2 to the n-half, such that there is no homogeneous set of size n. This implies that RT22 implies closure of the cut I01 under exponential function. So the base theory are polynomial functions and nothing else. But with RT22 you can prove very strong closure properties. By this fact and some classical results like shortening of cuts, and this is all written down in a survey by Pudlak, there is a proof in RC0 star plus RT22 of size only polynomial in n of the sentence that this monstrous number exists, where 2 with subscript n is exponential tower of height n. Then it is known that I delta 0 plus exp, in I delta 0 plus exp, you can prove that existence of this also very big number implies a finite consistency statement where con-X and some theory in brackets means that there is no proof of contradiction in this theory with fewer than X symbols. And so combining all of this gives you that RC0 star plus RT22 has proofs of size polynomial in n of sentences con 2 subscript n of I delta 0 plus X. So it proves with very short proofs finite consistency statements for very big arguments. And on the other hand, by the so-called finitistic Gödel's theorem, and the fact also proved by Leszek, Lawrence, and Keita that RC0 star is polynomially simulated by I delta 0 plus X, the shortest proof of this finite consistency statements in RC0 star is of size polynomial and this 2 subscript n. So this finite consistency statements is a family of sentences that are that have very short proofs with RT22, but have enormous proofs without it in RC0 star. And this is speed up of RT22. Okay, but here what is the key point of this slide is that this lower bound for finite RT22 is exponential. And yes. So we know quite a lot about RT22, and one may want to look at some of its combinatorial consequences. So over RC0, there is a whole business mostly at those principles. So this is a chain-antichain principle, ascending-descending sequence principle, and cohesive Ramsey theorem. Don't worry about those this ideas in CRT22. We will be occupied only with CAC. So what we learned about them over RC0 star is that some implications, well, not still hold. We don't know what's the case with implication from CAC to CRT22, but for now that's not that important. We learned that all these principles seem to have similar strength. So they are all pi3 conservative over RC0 star. And they are not fully conservative. So the first three are not pi4, and CRT22 is not pi5 conservative. And one would like to know whether they differ from each other, maybe in terms of proof size. And the clue that it might be the case are finite versions of those principles. So yeah, here you have finite RT22 and finite CAC, which say basically what you would expect them to say. And we are looking at CAC because it is the strongest of the principles from those that we studied. And as I said, the RT22 has exponential lower bound for its finite version, but CAC has only polynomial upper bound. So if you want, if you would like to have in a finite partial order a chain or anti-chain of size k, you need to consider a partial order only of size well, k square minus k, and it follows from Dilworth's theorem. So having this, you already see that the previous argument for RT22 will not go through. Yes, now I'm going to introduce to you forcing interpretations and firstly forcing translations. Some general notions for these methods. Yes, I'm slowing down a little bit because I'm changing for a moment topic a little bit. So maybe you would like me to go back to something and or stop. But if not, let us go with forcing translations. So if you have two languages, L and L prime, forcing translation tau from L to L prime consists of the following L prime formulas, which define a partially ordered set of forcing conditions, so the first two. Then a set of valid names. You define what it means that a forcing condition forces a name to be valid. And then you define what it means that the forcing condition forces some formula of some names. So yes, it's all syntactical work, but we actually keep in mind that there is some generic filter, and from it will determine our generic model. Yes, and then this definition of forcing formula is an inductive definition. So firstly, you say you define it for atoms and then extend for other formulas in standard way. So for example, we say that a condition forces negation of some formula phi if and only if there is no condition below it which forces formula phi. And then for implication, it is some, and for universal quantifier, there are some density conditions. Don't worry about that. I'm not going to bother you too much with those syntax. So now now I'm going to explain what is a forcing interpretation and how you can use it to prove non-speedup for some theory over another one. So suppose you have theory T and S, and gamma is a set of sentences in their common language. So the general pattern of a proof of non-speedup with forcing interpretation is this. So firstly, you construct a forcing translation, as on the previous slide, from the language of theory T into language S. Then you prove that this forcing have some nice properties, and most importantly that the rules of first order logic are forced. In particular, forcing double negation of a formula is equivalent to forcing that formula itself. Then you need to prove that this is a forcing interpretation of T. Well, to say that it is forcing translation is a forcing interpretation of some theory is just to say that every axiom of that theory is forced by every condition. But we want it to be polynomial. So this means that there exists a polynomial time algorithm, which given an axiom sigma of T outputs a proof in theory S of the sentence that every condition forces that axiom. And here I'm writing that every condition and not just the biggest one, which is usually denoted by 1, because we don't need to assume that there exists the biggest condition. Sometimes there is, sometimes not, but well, it doesn't matter. From this, it follows that given any proof delta of any sentence in T, one can find in polynomial time in length of this proof a proof in S of the sentence that every condition forces sigma. And then to obtain non-speedup, you need I call it polynomial time reflection theorem for the class gamma. Namely, you want to have a polynomial time algorithm which on input gamma from this bigger gamma returns a proof in S of the sentence that if every condition forces gamma, then gamma holds. And putting these two things together gives you a polynomial simulation of T in S. So that's the general scheme. Now some model theoretic intuition for our example of forcing interpretation. So idea is for forcing interpretation of CAC in a model of RC0 to find a generic proper cut in a model of RC0 satisfying a CAC and a given sigma 03 formula. So this is not new idea. It was very fruitful, for instance, for RT22 and conservation, pi3 conservation for RT22 over RC0 to perform a forcing construction model theoretically that is not formalized within theory, that you take a sigma 03 formula consistent with RC0 star. You take in a model of RC0 star a witness to the outer existential quantifier of this formula, and you build in steps a cut within this model, starting with this witness, which finally will satisfy your base theory. Well, in this case, we would like CAC. It was for RT22 and your formula. So such a proof is in a paper by Leszek and Keita, where they generalize a result of Patey and Yokoyama for RT22. And then Leszek, Lorenz, and Keita were able to formalize this construction to prove a polynomial simulation of RT22 by RC0. But here there is some problem. So in some models of RC0 star, there might be no proper cut close under exp containing a witness for the outer existential quantifier of a given sigma 03 sentence. Because it might be the case that exponential function can be iterated of a given element, say omega many times. So if you would like to iterate exp and some other function that would guarantee you that this sigma 03 formula would hold in your cut, then you would get to the top of your model. So no proper cut possible. But we may improve it, work a little bit more, and make this generic cut in 2 steps. So the first step will be non-confinal extension of the ground model, which will be a generic computable ultra power with a special proper cut needed for forcing construction in the next step. And in the next step, we basically will proceed as we wanted initially, but now this problem won't occur. So the yes, here will be the plan of the proof. But firstly, let me introduce an auxiliary theory: I delta 0 plus exp plus axiom SC in the first language of first order arithmetic augmented with unary first order predicate. And the axiom SC says that I is a proper cut close under multiplication. And for every number x, you can iterate exponential function on x more than cut many times. So there exists a number bigger than this cut, and C and result of iteration C many times exp on x. Yes, and the plan for the remaining part is this. So firstly, we forcing interpret this auxiliary theory in RCA0 star. This will be a generic computable ultra power with the special cut I. Then we will forcing interpret this intermediate theory. What I'm saying. Then we will interpret RCA0 star plus CAC in this intermediate theory, and this will be a generic cut. And finally, we will need some forcing lemmas to conclude that it gives us indeed a forcing polynomial simulation of RCA0 star plus CAC in the base theory. So basically, this will be about this polynomial reflection theorem.
Kasia, sorry, will you tell us more what these generic computable ultra powers are and generic cuts?
Of course, just in this next slide. So I will give some tactical definitions, but it will be I think immediately clear how it looks like when you're just interested in model of this kind. Yes. So just in few lines the definitions will appear. Here I would like you to note that the cut 0 I01 is always closed under multiplication, and we can and will assume that it is sigma 01 definable. If not, then we would get just a standard interpretation of this theory with SC axiom, because this cut then would be would satisfy axiom SC. It's quick. I'm not going to go deeper into that. Now I'm going to define this first forcing interpretation. So yeah, this is these are definition in our formal theory, but if you have a model of arithmetic and you're not worried about formalizing this ultra power, you just computable generic ultra power is obtained. Well, you consider partial order of delta 01 infinite delta 01 computable sets. And then you have some generic filter on that order, and yes, your model will your generic ultra power will be just the set of equivalence classes of computable total functions, and generic tells you which functions are equivalent. Those functions are, well, function f is equivalent to g if they are equal on a set that belongs to generic. And yeah, it is it clear? So
and the ordering on the conditions, is it subset?
Yeah, it's precisely. It's yeah, by being a subset. Yeah, order given by inclusion. So very early people.
May I ask something here, to make sure I'm understanding? Why would two names be equivalent if they are equal on a set in the generic? Because it's supposed to be total functions, not just total on the generic, but total on the entire model, I gather. So why would you want them to be considered equal if they're just equal on some set in the generic?
Yeah, this is how I define this ultra power. This generic filter allows me to define equivalence relation on the set of functions. You check that it is equivalence relation, and then you can define all operations order on this universe, which consists of equivalence classes.
Okay, I lost track of the fact you're building a generic ultra power.
Yeah.
Okay, good. Thank you.
So firstly, people consider arithmetical generic ultra power, where you just consider arithmetic sets, I guess. Yeah, but we work with this. So in our theory, forcing that V is a valid name is trivial. It always holds. Then we define forcing for atomic formulas. So it is also straightforward. So we say that some equality or inequality on terms of some names holds if it holds, well, it's forced if it holds on all but finitely many elements of this condition. So yeah, precisely as you would perform this construction model theoretically. But we need also to say what it means that the condition forces this new kind of atomic formulas, namely that some value of some term on names belongs to cat I. So this holds if there is if on all but finitely many elements of this condition, the value of that term on X is it's smaller than some element of cat. So if you
when you say finitely many, do you mean boundedly many?
I hope that I said all but finitely many.
But when you say by finitely, you mean boundedly or standardly finite?
No, boundedly many.
Okay.
Yeah. Yes. So our theory may not know anything about standard natural numbers, so we cannot. It might be not definable. Yes. So if you want to see this, this new cat, maybe this old cat I01 will be cofinal in this new cat I. This line says precisely that. So having this, we need well, I would say some version of Wash theorem, delta say Wash theorem for delta zero formulas, and it says that delta zero formula is forced by some condition, even only if this formula holds on all but finitely many elements of S. I'm not going to prove it. It's just induction on the complexity of a given formula, and the base step is guaranteed by the definition of tau1. And second lemma is to show that tau1 is actually a forcing interpretation of this theory. So to see that PA minus and exp are forced is rather immediate from the definition of tau1, and because it clearly holds in the ground model, then I delta 0, 1 is well, I delta 0 is proved with this previous lemma. And I would like you to demonstrate to you how our method works and show that axiom SC is forced. So firstly,
excuse me, could you please remind me of what SC says?
Yes, of course. I'm going to repeat it all in conjuncts of this sentence. So firstly, we need to show that that I is a cut. So initial segment closed under successor. And yeah, this is immediate by the definition of forcing and the fact that I01 is a cut. But we wanted it to be a proper cut, and that's more interesting. So we are going to find an element in our generic model that will be strictly above this cut I. So we define a total computable function D. Well, in our ground model, such a function exists like this. So recall that we assumed that I01 is sigma 01 definable. So we have this cofinal set A, which is delta 01. This set can be enumerated by the cut in increasing order. And we define function D on X to be the unique element of the cut such that X belongs to this interval. So remember, there was this picture on the left side of some few slides ago that this set A divides our universe into I many finite intervals. So the value on the number X of this function is just the number of the interval that X sits in. And yeah, it's quite late, so maybe I will skip it. But this is really simple to show that I think about this function as a diagonal of the cut I, that it's stretched along the whole universe. So it must be you see that this function agrees with a constant function equal to some element of the cut I01 only on finitely many coordinates, finitely many according to our model. Okay, so I'm going to skip that. Then we wanted to our cut I to be closed under multiplication, and it's immediate because the cut I01 is always closed under multiplication. And finally, we wanted to prove the following property, that you can, in your generic model, you can iterate exponential function on every element more than I many times. So there is a number above the cut I such that there exists that many iterations of exp on this number. And to see that it is forced, look at this function v. This function v will be in our generic the value of, well, d iterations of exp on v, where d is the function from the previous slide, this kind of diagonal of our cut. So in our ground model, you define V as follows. On X, V equals to ith iteration of X on V of X, where this I is again the index of the interval of this element X. And it is possible to define it this way because, well, I01 is sigma 01 definable, and yeah, and that's it about with the first forcing. Any questions to that? Okay. So now we have this generic ultra power. We don't need to think about this equivalence classes anymore. We just enjoy that we are in a model which satisfies this axiom SC. And now our conditions are finite sets with more than I many elements, which are additionally exponentially sparse, which means that if you enumerate in increasing order elements of such a set, x nth plus 1 element is greater than x of the previous element. Then names are just natural numbers, and for second order objects, they are just seen as codes for finite sets. And small letters are for first order names, capital letters for second order ones. And now forcing that something is a valid name is not trivial. So a condition forces that V is a valid name if intersection with this initial interval given by V is not a condition. So we think that of it as a small set. It has fewer than I many elements. And then forcing that a name for a set is a valid name always holds. Forcing relation for atomic formulas is trivial, so S forces that some phi holds if well if it forces about those names that are valid, and this formula holds in ground model. Then we have auxiliary lemma asserting delta zero elementarity, which basically says that, well, this trivial condition on forcing atomic formulas, you can extend it on all delta zero formulas. And then I'm going to convince you that this is indeed a forcing interpretation of CAC. I will focus on forcing this principle. The rest is either immediate or boring and also straightforward. Yeah, for PA minus it's immediate. With exp, why exp will hold in the generic? Well, because conditions are exponentially sparse. So we want to see that if a condition forces some name to be valid, that is, if it forces that some name will denote some element in your generic model, then this guy is a condition, because, well, intersection with this interval is not a condition, so the remaining part must be a condition. Then the conditions are exponentially sparse, and this means that exp of V will be not greater than minimum of this condition. So so this is again not a condition, and this means that S also forces about exp of V to be a valid name. So maybe not friendly notation if you haven't seen that before, but this is super easy. You just exp on some name that is valid will be just the next element in your condition or something close to it. So it will be forced to be valid by the same condition. Your condition remain big if you take from it numbers up to x of some name. Yeah, I skip induction. For induction, you will need that element delta zero elementarity, and I will give you idea why CAC is forced. So here I will finally use this polynomial upper bound on its finite version. So suppose that some condition forces that this order is a partial order on n. Well, this should be some letter variable. I wrote this with this symbol to indicate that we are talking about some partial order. Then you can split this condition into two other conditions, such that the first one is strictly below the second one, and that this order is defined on the whole as 1. And we want it to be defined on some condition, because here we cannot assume that it is defined in the ground model on S, but we can find a condition below such that it is defined on the whole that condition. And now the crucial thing is that by Dilworth's theorem, you can find a condition S star below this S1, which will be a chain or an anti-chain in this partial order. And yes, we also use here the fact that the cut SC is closed under multiplication. So this set S star will still have more than I many elements. And now by this delta zero elementarity, S star is forced to be a chain or anti-chain in this partial order. So here we looked at S star and S1 in our ground model, but S star will also be forced to be a chain or anti-chain in our generic. And then we check that this S star is unbounded in our generic model. So here it's yeah, nothing. I'm not going maybe to read that. You again convince yourself that it holds because you have your conditions are very big finite sets, and when you just take something from below, you still have a big finite set. That's just unfolding some definitions and nothing really smart. And yeah, so that's forcing CAC. And what is rest is to check that it indeed gives you a polynomial interpretation of RC0 star plus CAC. So first lemma to prove is that there is a polynomial time procedure that, given a proof of a sentence sigma in RC0 star plus CAC, outputs a proof of the sentence that the first forcing forces that the second forcing forces that sentence. And it is tedious, but nothing special. And then this polynomial time reflection theorem, which says that there is a polynomial time procedure that, given sigma 0 3 sentence, well, here eta, outputs a proof in RC0 star of the sentence that if eta holds, then first forcing forces, that there is a condition in second forcing that forces eta. And yeah, so this is syntactical version of the way that you prove pi3 conservativity of, say, RT22 over RC0 or whatever. there is idea of the proof, but I think that I used my time, and here again you work with this diagonal of cut I01, and you just define this this set that will be a condition in second forcing that will force what you want to be forced. And yeah, basically that's it. Here are some references, so I would like to you to give some attention to this paper by Leszek, where is it? Leszek, Lawrence, and Keita, where they proved well, polynomial simulation for RT22 over RC0 and speed up over RC0 star. Very, very nice paper. Yeah, the method of forcing interpretation was developed by Jeremy Avigat in this paper and also in his PhD thesis, and he used it to get the quantitative strengthening of a classical result that WKL0 is arithmetically conservative 0. So he formalized this forcing construction inside theory and obtained that WKL0 is polynomially simulated by RC0. Yeah, so that's it. Thank you very much for your attention, and if you have any questions, please do ask.
Okay, thank you. Let's all thank our speaker. I think that was great. Really enjoyed that. Are there yeah, just go ahead and feel free to unmute if you have any questions.
Can I ask a question?
Go ahead.
So the first forcing is like the some kind of ultra power. So the second one, can we also view it as some kind of like ultra power?
The second? No, the second.
Yes, the second forcing.
The second forcing was building a generic cut inside inside a model of this I delta 0 plus x plus SC.
So
because there was this maybe, you know, I will change my presentation for a moment because I have it without pauses, so it will be easier to go back to some slides. Yeah. Okay. Can you see the slides again?
yes.
Yeah. So sorry for quick. I need to move this pan. Okay. So here you have this. Yeah, the initial idea was to just to find a generic cut in a model of RC0 star, but there are some general reasons that it might be impossible to find such a cut. But in the we construct this intermediate model, which is generic computable ultra power, so that we can in the end find that generic cut. And if you want to see something in a structure, it is so you are in this model of well, I delta 0 plus x plus SC, and you start with a big finite set, those sets that are conditions in our second forcing, and you your generic you go along your generic, and you have smaller and smaller but still big finite sets which are, you know, the n+1 finite set is contained in nth set. They are smaller and smaller. And then your generic cut will be subpremium of the given by the smallest elements of your finite set, of your forcing conditions. This is how it is done in a purely model theoretic construction, for instance, in paper by Leszek and Keita on RT22.
Okay, thank you. So is it like some coded ultra power thing?
Sorry?
Is it like some coded ultra power?
What kind of
I'm not
ultra?
sure whether I understand correctly. Okay, thank you anyway.
Yeah, thank you.
Okay. Other question? Okay, I'll take this time to ask something myself. So, is there some sort of at some point there were these two results that you mentioned. One was about polynomials assimilating one theory and another, and one was about speed up. And is there so this one, I suppose they're somewhat opposed to each other, and so I want to know how the result for speed up actually what that result was. Maybe I misread it.
Well, for RT22.
Oh, I see. It was not. It didn't involve CAC at all. Okay.
Yeah, because well, actually, that was the only speed up argument that I
see. Oh, okay.
Yeah, you mean this one?
I see. Okay, this was the one that you.
Yeah, so
RT2 has speed.
No, very rough idea.
Okay. Okay, I see. So that was my confusion. I missed that this was about an entirely different theory. That's okay.
Okay.
Thanks.
Yes.
Okay. Other questions?
And by I said that this polynomial simulation of RT22 by RC0 is also obtained by forcing interpretation in earlier work by Leszek, Lorenz, and Keita. So they do a very similar thing, even more complex than this work of mine. They also force some generic cut in a model of RC0, but they use this alpha large finite sets. So they actually formalize earlier construction of Leszek and Keita within RC0.
Okay. Other questions? Okay, let's thank our speaker again. This was a great talk. Thank you again, Kasia.
Thank you very much.
And next week we have one more meeting, returning to a normal time, 1 p.m. New York time. Mateusz Welik, also from Warsaw, will be speaking, and the details will be on the website soon.